Hi, everyone. Thanks for having me. This is the first time I've been at Supercompute. So I'm going to start by saying that at IBM, we're all in building what we call quantum-centric supercomputing. I'm going to go in and tell you about what it is and show you some examples and show where I think HPC and quantum is the only way to achieve this goal. So I don't need to tell HPC people, but you've been on a journey for a very long time, from CPUs to vector machines to massively parallel machines to micro and to GPUs. On quantum, we've been following a journey on making the technology exist, showing fundamental principles. Last year, in 2016, we put a IBM quantum computer on the cloud, and then we built large-scale quantum computers, achieved this thing called what I call quantum utility, and now I'm going to show you workloads for quantum-centric supercomputing. But to take a step back, why quantum? Well, it is the only technology where the math is entirely different, where it's branched. It's a new form of math, a new form of primitive, and from a complexity, we know that essentially problems that we thought were hard on a classical computer can become easy. Most famous is factoring. Other examples are simulating quantum mechanical properties. And so quantum opens this lens of looking at a new set of problems. For those that don't know what quantum is but have a grounding in classical, I like to think of quantum as just putting negative signs on essentially probabilistic vectors. So if you understand classical, you'll have a bit, you can have a probabilistic vector. If it's stochastic, you can have an exponential matrix that encodes it, but we all know that classical evolution can be written in terms of an efficient way to handle that exponential, whereas in quantum, you get this thing we call quantum phase. People in the community call it superposition. Through superposition, we create entanglement, and there's no way that we can simulate this effect of this exponential, and it leads to us doing correlations. From an operational perspective, what we do is we execute this thing we call a quantum circuit. And a quantum circuit is just a coherent set of operations. Those in classical that know reversible computing, think of it as very similar to that. It's reversible. Most of those coherent operations, whether they're the superposition gate we call the Hadamard, C0 that generates entanglement, can basically be implemented, and we do basically a bunch of qubits. You can think of this as your memory, and then we do the gates as a function of time, and you can think of these as your operations. Of course, we can insert what we call irreversible steps that allow us not to change the complexity class of what's possible with a quantum computer, but it potentially makes things easy. This example is showing teleportation. So think of the quantum circuit as the unit. And we actually know a lot of applications of quantum computing. I go around and people always ask, what is a quantum computing going to do? You can find, you can go to the quantum zoo, you can find applications. But the truth is, I wanted to point out two regions. So if we've got the circuit size, the number of gates in that circuit, and the circuit width, if you're below 100 qubits, you can simulate it on a classical computer. And in my opinion, you're wasting your time just even experimenting with anything less than 100 qubits. If you're less than 1,000 gates, again, you can simulate it with a different type of technique. So this shaded regime I call pre-utility. Now, of course, we have these applications, whether it's for spin systems, chemistry, materials, cryptography, optimization, and they require a lot of operations. But there's this white space. And the truth is, where we are with this technology is in just crossing this boundary, just crossing what I call utility, which I'll define in a minute. And so this is exciting because this white space is where we want to explore and look at some type of applications. That being said, IBM has a roadmap. The roadmap goes out for 10 years. It includes realizing what we call in the field a fault-tolerant quantum computer in 2029 and a larger one in 2033 that is capable of doing those algorithms I showed on the previous page. The two things I want you to get when you look at this roadmap is first, that we've executed everything that we said since we started putting the roadmap out in 2020. And we're building up the stack to make programming and bringing classical and quantum computing together to create this quantum-centric supercomputing vision that I'll go in to realize that. So we have a roadmap to get those large algorithms from before, but in the near term, we actually have proofs. I love this paper. The paper was from a few years ago. What it actually showed was you can prove a separation between classical and quantum even for short circuits. It turned out this was a game. It's a typical game. It's not that relevant. But as you extend this, the field has basically found many different ways of giving you a view of what it means to be difficult for running on a quantum computer. And my view is the complexity hardness of the circuit is the only reason you want to actually look and find a quantum application, and that's where we're going to find quantum advantage. Now, there's one approach to quantum advantage. I'm going to call this, there's two approaches. I'm going to jump into the first, the sampling approach. The idea here is that a quantum computer just executes some circuit and then gets some bit strings. Famously, Google demonstrated this a few years ago. From a theoretical complexity point of view, I actually find this great. This paper by Scott Aronson actually established the hardness of this problem. The actual problem with this method is, in my view, three things. One, it's very hard to actually verify that this circuit is actually hard. However, there's new ideas that have come up with peak circuits that come into this that could be potentially. The second is it's very hard to actually certify the outcome from this circuit is actually accurate. So you can't really believe its outcome. And third, and this one is saying even in the presence of noise, the samples will be corrupted, but some of those samples will lead to, that will lead to a polynomial efficient algorithm to do it. However, this polynomial has basically a scaling that goes as 2 to 1 over the gate error epsilon. So even for 10 to the negative 2 error rates, that's a 2 to the 100, which is already, doesn't make it actually useful. The approach that we took at IBM, I call it the observable approach. And so in this, for this near term, I want to start slightly different. I want to say, I'm going to give you a circuit. I'm going to give you a set of observables. I'm going to run them on a quantum computer. But I'm going to come up with algorithms and procedures that guarantee accuracy to give you error bars. We called this error mitigation because I wanted it to refer to something different than error correction, but the goal was to give you accuracy. The cons of this is the runtime is now not polynomial, it's exponential. Secondly, there also exist polynomial algorithms that could look at this. And third, the hardness of this cannot be put on the same grounding as the hardness of the sampling of random circuits. And I'll go and jump through these three to give you a feel. So first, we've been making a lot of progress experimentally, demonstrating error mitigation, making bigger circuits, showing that it scales, getting to very large circuits. But to kind of jump in and give you a view, and for those that don't know quantum math, I'll give you a little bit of a high level. Essentially, you have these circuits that are represented, and they go from basically from the left all the way across to the right. They apply some unitary operation, and usually there'll be some noise lambda, and then there'll be some recovery that we want to do, like cancel the error, okay? And we'll do this iterative many times. Error correction is the only way that we know that that recovery map can be implemented to give you basically an efficient single-shot realization of this. However, the things are required to implement error correction. I can do a whole talk on that. I'm not going to, but I'm just going to say there's 5 things that need to be done. No one has done them, no matter what you read. Error correction has still got a lot to be done to get all of them, and that's why it's going to take us to 229 to actually do it. Okay, so the other way you can actually implement this recovery map is you can say, well, can I resample it so that I can add different circuits together to effectively remove it? Another way is you can do post-selection, throw out a lot of the results and only keep the ones that you like, or you can do a combination of them. And there are also theory papers that show those come together. So all of these fields of, all these things of error mitigation, error correction, they're all based on the same idea of implementing a circuit and implementing it in a way that we cancel the effect of the noise. You can do a Hoffing's bound and get those error bars I said for error mitigation. I'm not going to go into the details other than say some quantity A, some noisy quantity AN, can be bounded by a parameter that goes, we call it gamma bar to the ND, okay? And so you see that this gamma bar to the ND is exponential. So we've always known that this runtime is exponential. In fact, the runtime J is gamma bar to the ND times some rate at which I do circuits times the depth. And you can intuitively view this gamma as 1 plus a small epsilon, okay? In fact, in the theory paper that we originally did this, we pointed out that essentially you find these runtimes are like 1 plus some small parameter epsilon to L. I apologize for the notation in our field. We seem to use all over the place. L here is just N times D. So in this sort of error mitigation, this independence, this ability to run these is independent of the circuit. It gives you a way to get error bars. It gives you a weak exponential. Of course, there have been now many different other papers that have proved as well this exponential runtime, and many times it's given as an example of why it doesn't work, but they all actually get essentially the same parameter, the same formula as some error rate to the power of the number of qubits by the depth of the circuit, so the number of layers in it. So you might think then that this error mitigation is dead on arrival. Let me put a few numbers. So if I want to say 100 qubits and a depth of 100, if I take an E epsilon, an error rate of 10 to the negative 2, we find that 1 plus epsilon to the n squared is essentially 2 to the 144. Definitely outside of what we can actually possibly even envision from a runtime running in anyone's lifetime ever. But if you do the same for this polynomial that is n to the 1 on epsilon, you actually find the same. It's a ridiculously big number. But if we make a factor of 10 improvement in the error rate, this comes down to 2 to the 15. The other one goes up to 2 to the 660. If you make another factor of 10 in the error rate, it actually comes down to 2 to the 2, and the other one is 2 to the ridiculously big number. So the fact that even though there exist polynomial errors, algorithms to simulate them, the polynomials scale so badly that they make them impractical, the exponential, as we improve our error rates, actually gets them down to a runtime that actually can make them run and give you accurate results. And if I compare where our errors are on the system, we see we're right in that range. We are now crossing 10 to the negative 3 and hitting down towards 10 to the negative 4. So for the two cons of its exponential to runtime and there exists a polynomial, I can get you accurate results, one, on a quantum computer in a reasonable amount of time. So from a kind of view of trying to understand the complexity side, and I'll come back to this later. Imagine you're doing some type of configuration. I give you some configurations, and you're searching over this configuration using a decision tree. You'll connect all these different parts, and you may use a lot more. What I've plotted here is down the number of useful configurations relative to the total number, until you get to an error bar of estimating some quantity, some observable, and I've plotted the error. You may use a lot before it actually comes down. What we can actually show with a quantum circuit is it can project you into those configurations. We can numerically do it, and we can show that it actually best uses these configurations and allows you to give that sort of view. So this sort of notion of a quantum circuit projecting, helping you find, is where we see this sort of areas to look for advantage. We've also looked at circuits in optimization, where we can actually come up, this is a famous paper by Ed Fiery, look at optimization, where you can come up with circuits that will be potentially useful for these problems. My team at IBM has looked at what we call hardware efficient circuits that can be used in chemistry, and what we call correlation circuits, which can be used in machine learning. So there's all these circuits that are sort of filling up this belief that they're hard. But last year, a big result happened from our perspective. We were able, the first time, to be able to run on a quantum computer an accurate quantum circuit on 127 qubits and approximately 3,000 gates, which is well beyond brute force classical computation. It cannot be simulated exactly using a classical computer. I'm going to give you a little trivial example. So here, if it comes up, sorry, animations are not working. I have a bunch of 10 different black boxes here. Each one of these is going to represent a different experiment. and I'm going to plot a parameter on the axis I call z, and a parameter on the x-axis I call theta, and I'm going to show basically each one of these gives a different value, okay? All of them are different. None of them are the same. What is truly, and in fact, if I take a sort of 80% confidence on them, they're about 20% different. What is truly amazing is one of these is actually a quantum computer. And this is what we meant by utility. It is able to run a computation where the leading tensor methods all give different results. I cannot tell you which one of these is more accurate than the other, okay? We're now at a point with our quantum computers at this scale that we can view them as a scientific tool. And even more, the methods, the new methods they're inventing in tensor methods are getting convergence. They're doing convergence, reliability, based on converging to an experiment. So quantum is at the point that the new improvements in these tensor methods are using the convergence criteria to be that it realized what was in a quantum computer. And so what we mean by utility is we're at a point where we cross and we have an exponential scaling. It's a weak exponential. It's not, we have to get error mitigation to error correction working, but we're at a point where we can now run circuits and I can give you accurate results that are beyond what you can actually simulate with your brute force classical computing. So 2 years ago, we set the goal that we wanted to actually get to a point where we could run circuits of 100 qubits, depths of 100, whether you wanted to go by 100 by 100 or total number of gates is around 5,000, and basically get accurate results on a quantum computer. And I'm happy to report that this is possible. So here's a circuit of about 5,000 gates, and it's essentially running a very simplified circuit. It does some type of trotterization and then mirror trotterization, so I know the outcome. But 60% of the 1 qubit observables on this circuit I can get with an accuracy of 10%, and this is what we set on that challenge of getting to 5K. Other methods, so here's a method by one of our partners, sorry, I looked at the wrong slide. And then even more improved results are emerging, where this is going up to 97, these are still research. The blue you can actually run using our systems on the cloud today. The pink method is new research that we'll bring out soon. Our partners are also developing what we call, another form of error mitigation. And this error mitigation is called tensor method error mitigation. And essentially you have the noisy circuit, and now what you do is you run a tensor simulation of something that is almost equal to the identity. So something that is easy to contract because you go from the middle out to allow you to get an accurate result. And in fact, it has a better sampling than the other methods, but it does require actually using GPUs or HPC to actually do that simulation. And doing this, we can even look at different types of circuits and again get around the 5,000K, and we can go to a point where those circuits have an analytical solution, we can verify that they work, and then we can go beyond where we can't do a brute force, and we find that some of the tensor methods agree with what we get on a quantum computer, and others don't, so confirming that we're in this new regime. So now I want to switch slightly to a little bit different and kind of get what I mean by another form of quantum error correction that is definitely suited for what, let's say, the quantum-centric supercomputing architecture. In this, I want to look at a chemistry problem, say Fe4S4. If you are going to do a fault-tolerant implementation of this, you'll have to do what is known as phase estimation through the estimation of the phase, get the accurate results. But it's going to require error correction in about 5 million qubits. And if you do some estimates, it'll take about 13 days to run. If you were going to do the trivial way of essentially error mitigating every term in the Hamiltonian, so there's 6.7 million operators in this Hamiltonian, it would actually take 3 million years for us to run the error mitigation things. And so again, that's another example of something that I would say is not practical. However, I'm going to show you a method that projects a quantum computer into a lower subspace and then allows us to feed it into a large classical computer and get this runtime down to about 2 hours. So we take a circuit This circuit has some chemistry properties that I don't have time to go in, but it sort of represents basically hitting it with different types of coupled cluster approximations and allows me to look at those, say, fermionic problems like the chemistry that I put up on the, like iron sulfur. Then what we do is we essentially sample this based on our quantum computer. So we run it on the Heron processor, and then we put all of this data into Fugaku, which is a supercomputer in Japan, and then we do what we call a configuration recovery. We look at a set of observables, we take that configuration, we diagonalize it, so do an advanced diagonalization method on the supercomputer, iterate, see what the occupation numbers come, and iterate that many, many times. And what is really cool is following this method, we are able to reconstruct chemistry molecule things, so like N2, which I would argue most people thought would not be possible. The quantum in the brownie color works better than the approximate methods like Hartree-Fock and the classical methods, say the blue and the yellow, and sort of represents the distillation more accurately. It also, as we scale up to iron 2, sulfur 2, it gets to the point that we're getting to the same accuracy as you would get with leading chemistry methods like DMRG. So those that are chemists in the field know these methods. I am not saying we're beating it. I'm saying at this point, we're getting to the point that we get close. If we go a little bit further into a bigger molecule, we get better than random sampling, but we're still, the noise in the system is stopping it to work. And so this sort of points out as we make improvements in the noise, this was run with about 3,000 gates, things will get better. In fact, this same method, because of the versatility it can, and the way that we are developing in a way where all of the software is open source, can easily be added to different types of problems. And our partners at Cleveland Clinic, Lockheed Martin have looked at different types of simulations, whether it's from water diameter to molecules that are for propulsion and other types of things. Okay? So the method is definitely stable, it works, and it's starting to go through different types of examples. And then as we've made improvements in the device fidelity, as I told you before, we've just recently been able to get this method to 5,000 gates. And so my view is we're now at the point that we have a quantum computer that can give you accurate results at 5,000, which is beyond brute force, and then there's an interesting question of how we start to use it. And that's where we lead into what I call quantum-centric supercomputing. And to me, it's not just a larger quantum computer. It's actually what I think of is the next generation of QPUs, GPUs, and CPUs all working together. And from a workload management, honestly, it's exactly the same. You have some type of graph that represents the problem. You have now, instead of having all of them be classical nodes, you have one node that represents a quantum that executes some type of primitive. And so you can fit it within the standard workload management systems you all know. In fact, you can go even further and say some of the jobs will always use the quantum computers, some of the jobs will use hybrid. I'll need to mix it through these type of hybrid where there's single jobs as well, and I may even want to do it direct access with a quantum computer co-located or through a cloud. And so that leads to what we're developing, essentially quantum cloud bursting, where you can send many jobs directly to the quantum computers, as well as direct access type where the same API, the same primitives that are run are used in both places. So we've started to prototype this as an example with RPI, who has AMOS, which is a large classical supercomputer, and also one of our quantum computers. They're actually stored close, and basically it's the perfect test bed. So we can start to do Slurm-like iterations, but because we have a bunch of quantum users that are very used to using the Python code, we want that to look like it's just how they would just work any day. So in this simulation here at the start, it showed standard way of setting up a Python job, and then it showed the Slurm integration as it went forward. So from the quantum users, it doesn't look any different. From the HPC users, it can just fit directly into the same way you're doing it. So this prototype is already working. We can run submission of jobs. You can have the mapping problem, the optimization, the pre-processing all running on classical nodes. You can have the execution of the quantum primitives, calling the VPN, allowing you to execute this sort of seamlessly environment. And so the take home I want to say is we don't actually have to invent anything. We just have to put these together, and we can actually start doing these workloads now. We are also working with our partners at Recon and installing a quantum computer right next to Fugaku, so we can even explore even faster connections between the two systems and look at extensions to the algorithm I talked about earlier. We're also partnering with Pascal because this architecture is fitting within the same way HPC is done. You can put any type of quantum computer there. You can create heterogeneous essentially heterogeneous QPUs mixed with classical and have this total architecture worked out. So my prediction is quantum advantage, where we can do something cheaper, faster, or more efficient than classical. And I know I showed you that I could run quantum circuits better than classical, but we all know classical methods are very good at actually solving problems without running quantum circuits. Quantum advantage means I can actually do it cheaper or faster or more efficient than any classical method. But I do believe this is only going to be possible if the HPC community and the quantum community come and start working together. And so I laid out a few things here. So before 3K, or less than 100 qubits, don't waste your time. Just do not waste your time. It can be simulated. It's cheaper to use a simulator. It's not interesting. In this error mitigation regime, where I can give you accurate results, you can start to look at approximate methods. And then we see the future as this continuous path to error correction and allowing us to realize large-scale error correction. I'll make a side note. I disagree with everyone that HPC is needed for error correction. Error correction is a very simple algorithm. The overhead and complexities of error correction are in building the size of the chips and getting reliability. So from a HPC perspective, I see it integrating in different ways. So first, I don't see any value in simulating wave functions. If you are going to spend a lot of money to create a cluster to simulate a wave function, it is not going to teach you anything about quantum computing. However, I do see a lot of value in the future being tensors plus circuits working together to allow us to do a lot more. So we want to create this simplified code that brings this future of tensors and circuits together. And one way you can imagine this is if you were going to use tensor methods, rather than simulating the quantum experiments we do, how do we as a community start to identify which ones of those tensors and which ones of those circuits are actually the hard ones for the tensor methods to do, so that we can use those error mitigation techniques that work for any type of circuit and actually start to build collections of circuits and observable pairs that can be like the toolbox for exploring how to use quantum advantage. And I do think quantum advantage is going to be the union of these circuits that I can run faster than I can simulate on a classical computer, as well as those mapping collections between circuits and observables that I've determined are the right candidates to actually not use tensor methods for. Error mitigation, because we are doing tensor methods on top, or large-scale diagonalization, or we even have lots of data handling, or we even have more robust, improving error mitigation techniques with HPC, making them more efficient, making them run faster, making them actually give us the same quality result using less calls to the quantum computer. These are all open questions of how do we actually extend, how do we bring numerical methods to quantum computing. Kind of talked about before, I do think the community in quantum, it is a myth that a single quantum circuit is going to be how we run a quantum algorithm. I do believe every quantum circuit needs to be more than 100 qubits, more than 5,000 gates, as I said. But the future is going to be running clusters of quantum circuits that you glue together with various different techniques, such as circuit cutting, one that we call matrix product. Forget the last letter, but essentially you use a tensor method to infer how you add those methods together to create a larger, more accurate quantum computer. And so when I go and finish on our roadmap, we have a roadmap, as I said, that will take us from today. We're going to make larger and larger quantum circuits. So this is what we have in 5K. We've achieved 5K. Going to 2026, I want to get to 7.5, 10K, 15K. Error correction will allow me to go up to 100 million. So you can think of this as how large a quantum circuit is run. But from the HPC perspective, as we go forward, how we do the scalable circuit knitting, how we do intelligent, how we do resource management, how we do circuit knitting in more of a product lens, and how do we create this collection of circuits and observables that we should be using as the primitives to define the algorithms is what we're going to do over the next couple of years. And so on that, I hope I've convinced you that quantum is at a point now that you cannot use a brute force classical computer to simulate it. I can give you accuracy and reliability, and this is what we call utility. To get to quantum advantage, we have to mix that utility with smart ideas and tensor methods, algorithm development to get us to the final goal. And on that, I want to thank you.
All right, you know the drill. Come to the microphones and ask some questions. Please.
Williams. I'm a researcher in tensor network methods for circuit knitting. I'm curious, as we move past this regime where we're able to simulate even approximately the quantum computers, what types of new methods will we need in tensors or otherwise to perform validation, benchmarking, and design of these systems?
So most of the time that you can do the validation, you exist in either efficient analytical solutions or efficient polynomial algorithms that allow you to do it, and then you move beyond. Rather than going to small qubits and scaling up, you go to points where I can predict it. In fact, we are releasing a tool that we call NEAT that shows you how you can take your circuit, you can put it into a regime where there exists an efficient polynomial algorithm, allow you to verify it, and then allow you to go away. This is exactly the same as what people do in numerics. Forgetting quantum, like just get quantum out of the word. You do numerical methods where you can validate the numerical method where you know you've got analytical solutions, and then provided I can give you error bars, or I can give you error propagation, whether it's infinite differences or those type of things, you can trust how it goes. And so my view is with error mitigation, because I can give you error bars and I can put things on there, you can trust that outcome to go beyond those type of methods. I actually think a better use of tensors is to think of tensors and circuits as equal partners and ask, how do we actually join them together? Circuit cutting is one example, but I think tensor contractions and tensor expansions, imagine that even some of the nodes turn out to be quantum circuits. And as we go forward, rather than using tensor methods to claim you can simulate quantum, switch it to tensor methods on top of circuits to expand what, I fundamentally believe the math of the future is tensors and circuits. And we need to think of them as primitives, and we need to work out scientific methods that use these primitives and add them together in different ways. And I think there's heaps of ideas, like you mentioned, circuit cutting. I think the validation, there are better methods to validation.
Thank you.
Okay, let's go to the center.
Hi, Tom Marseille with Washington and Lee University. We've heard a lot this afternoon about how we're looking at hybrid computing with quantum and high performance computing. IBM has been a leader in both quantum computing, but also has a very long history in supercomputing. And right now we're hearing a lot about how we're just going to create quantum nodes and we're going to just add this on to existing supercomputers. And I'm wondering if IBM has considered actually merging their divisions of supercomputing and quantum computing and developing a system from the ground up so that all of that integration is built in and being considered and engineered together.
We are very connected between the different parts of IBM. We share that the future of computing is these different things, like I said, tensors plus transactions, like summing numbers, plus circuits. If you want, it's bits, neurons, and qubits as a simple way. Just that what we are envisioning with the quantum-centric, yes, I showed you realizations that we just were integrating it with standard HPC. As we explore different types of tensors and tensor accelerators, I am 100% sure the future will be tensor accelerators mixed with circuit accelerators to get to that vision. I share that vision, and that is the goalpost. But we put it all under this umbrella of quantum-centric supercomputing, but there's a long path to do it. And I think what is cool now is quantum should now be considered part of that equation. With the utility type experiment and giving you accuracy and doing it at this type of scale, it now has almost like graduated to be at that. And so that was only last year. Our goal over the next, well, probably as long as I stay at IBM, is to bring all these together and realize a quantum-centric supercomputer that brings forward the math of the future. Well, I shouldn't say math, the realization of math that we've always known. Like quantum math has been known since I don't know, Schrodinger, Einstein, and all that. But the math that can now be realized at scale, and we've got to work out how we put algorithms to these things. And I think that's the exciting part. And what I wanted to get across in my talk is we're at the point where we can, like, maybe I'm too much of a physicist, but I can put error bars. I can give you numerical confidence. And so now we can start to build that. And I know I'm not directly answering your question because I also believe some of that, how it comes together, even though we show it's easy to integrate with the Slurm or the tools, you can just do it, has to be driven by the algorithms that we discover that use these two types of math.
Thank you.
Hi, my name is Tanya. I have a PhD in physics. You emphasized over and over that anything less than 100 qubits should be classically simulable. I have a paper right here on a 56-qubit machine from Quantinuum. I'm going to read you a sentence from the abstract.
It's an exponential. So I think the world record is 45 qubits. I'm making the point that 100 puts me above any innovation that happens in the classical world. It is extremely, extremely unlikely that anyone is going to get to 100. Maybe they'll get, the record now is 45. Maybe they'll get to 54. Maybe they'll get to 60. But that exponential just kills it, that you can think of 100 as a mark, that you're just safe, that you're setting enough. I think that is, where exactly that number is, I honestly don't really care too much. Whether it's 45 or 54, it's an exponential.
I'm not sure what you mean it's an exponential. I think that they've showed that at 56 qubits, they're no longer classically simulable, which contradicts what you said. Can you help me understand?
So 45 qubits is the exact, I think that is the record that people have done using a method called the Schrodinger method of simulating the wave function exactly. I don't know what the record is using the Feynman method, but that is actually the dimension. So if you really want to go from an exact brute force method, you draw a 2D plot. You have 45 qubits and essentially very, very long depth. So let's put that point. You have many, many qubits.
Are you talking about simulability?
Pardon?
Are you talking about classical simulability?
Yes, that's
okay.
That's what they're saying is. And if you want to draw the line at 56, I'm okay. 100, it's not 100. with a depth of 3,000, no amount of energy using classical will be able to simulate that. Unless it's an approximate
but I think it's
tensor
clear that at 56, it's no longer classically simulable.
They need to give you the depth, and if you do a Feynman method, I am not as comfortable saying 56 will not be done from my perspective. If they want to say it, let them, I don't care. I have set my boundary at 100 and 3,000. If you want a smaller boundary, like I said, the record is 45 for very long depths. I do not remember what the record is for the Feynman method. Don't remember off the top of my head. But I can tell you, you can do 10,000 qubits as a short depth. So you got this contour. And 100 by 3,000 is so far into that contour of not being able to be directly simulatable that you don't even bother trying.
Understood, but I don't think you're wasting your time at less than 100 qubits, which is something you did say. Thank you.
Have fun.
Hi, Eddie Zhang from Rutgers University. So I have a question that's related to AI. Do you think if AI can scale up the kind of applications that can take advantage of noisy quantum computers we have today? You mentioned an application that can predict accurately using 127 qubits and 2,880 gates in your slides. So do you think we can go beyond that for this NISQ era devices? And if AI can help us achieve that goal? And if so, how and how that, which aspects?
Already I showed you 5,000, so we're already beyond it. We have online a AI-powered transpiler service that can help you compile your circuits much more. I am very much a fan of AI helping quantum to simplify how you set up your quantum circuits, or how you determine better ways of sort of breaking up the problem. How all these mix together is related to my point of this future being tensors and circuits.
Right. So, so we are at the HPC conference. So, if you think AI for quantum is useful, do you think it would need a HPC or supercomputers to achieve that goal?
I think you will need supercomputers for extending the methods of handling the errors and how you break up the problems. I think supercomputers for the compilation is definitely valid. Exactly the scale of that is part of the work. We're seeing some of these tensor methods allow us to do these more advanced circuit knitting that with this MPF. You could think of this as a great use case for HPC as well.
Okay, I see. Thank you.
Okay. I'll ask a question while everybody's thinking of their next burning question. So you had mentioned HPC for compilation. As the quantum circuits or the quantum systems get larger and larger, is there a point at which we won't have a supercomputer big enough to compile for a quantum computer?
Most of the compilation is going to be heuristics, and I imagine doing similar things that we do in the classical world with peephole and things like this. So you give more resources, you throw at it, make it better, but you're probably going to do just as good with a lot of these heuristic compilation methods, exactly the same as what exists in the classical world.
But do you think that maybe there would be a quality threshold, that as the quantum systems get larger, you need the HPC system to compile for it. At some point, you have to use the heuristics, like you just said. But then do the heuristics get worse and worse as the system gets larger and larger?
I think the scaling is going to be in your favor, because even if you could do a little bit worse, the exponential scaling on what quantum does will overweigh that. But it's a great question. It's an open question. I don't know the exact answer, but I don't think compiling future quantum systems, quantum computers, is going to be limited by our smartness and our classical resources. I think there's a lot of intelligent people and methods that we have to put together to make the compiling problem happen.
Okay. We have a question over here.
Yeah, Sergey Glazer, University of Alabama. Thank you very much for this amazing and visionary talk. Maybe expanding on the last question, I know you mentioned AI for control and things like that. What about quantum machine learning and algorithms that directly take advantage of the circuits and design them for the circuits and to take the best advantage of the QC?
Using AI to design better circuits?
No, I'm talking about directly, like algorithms, machine learning algorithms that are directly in the language of circuits. So like quantum transformers, quantum graph nodes, things like this. Quantum machine learning, like directly.
So I showed a paper by my personal algorithms that I'm interested in doing, quantum algorithms for AI. I showed a paper where we look at data that from a classical lens, you would say it's random. And there exist quantum algorithms that could tell you that that data was not random. And we've started to explore that. It's hard to really formalize that, but we call this quantum kernels and quantum machine learning. I think this is a great, exciting research direction on how we can get quantum algorithms for AI. I don't think it's going to be helping in any way big data. I think it's going to be helping when the data has some type of correlation that is, from a classical lens, you would say it's a random number.
We're starting to see also advantage in that space, but again, in a very niche scenario, small models, small data, that kind of scenario.
I think quantum machine learning is great.
Okay, I have to apologize that we are out of time. So let's thank Dr. Jay Gambetta for this really exciting talk. Thank you.